Hello and welcome to the Hospital Near Me Medical Career Training Channel. Today we are working on the Medical College Admissions Test or MCAT to get you into medical school. Today's featured hospital is Ellis Hospital. Their address is 1101 Knott Street, Schenectady, NY 12308. Their main number 518.243.4000, information 518.243.4366, and emergency 518-243.4121. Today, we're diving into essential chemistry topics, exploring how atoms bond, what happens during combustion, the significance of oxidation in reactions, the science behind nuclear fission and decay, and even how radioactive particles are used in cancer treatment. Let's start our journey into the fascinating world of chemistry. Join us in this educational journey through fundamental chemistry concepts. We'll delve into combustion, atom bonding, oxidation in reactions, nuclear fission, nuclear decay, pH equations, and the use of radioactive particles in cancer treatment. Do you need to talk to someone? Get confidential help through talking with a full-services professional listening company. Reduce your stress and increase your peace. Get problem-solving help today. Click on the link in the description that says, "Let me help you in life." Increase your peace. Get problem-solving help today. Question 1. Combustion. Let's kick things off with combustion. Learn about this rapid chemical reaction involving oxygen that produces heat and light. Understanding combustion equations is crucial for the MCAT, Medical College Admission Test, as it assesses your knowledge in various scientific disciplines, including chemistry. Here's a college-level explanation of combustion equations that may appear on the MCAT. Combustion equations. Combustion is a chemical reaction between a fuel and an oxidant, typically oxygen gas, that produces heat and light. In the context of organic chemistry, combustion often involves hydrocarbons, compounds consisting of hydrogen and carbon atoms. The general form of a combustion reaction for a hydrocarbon fuel can be represented as follows. Fuel, hydrocarbon, plus oxygen, carbon dioxide plus water, energy. Fuel, hydrocarbon, plus oxygen, carbon dioxide plus water plus energy. Here's a more specific example using methane CH4 as the hydrocarbon fuel. CH4G2O2G CO2 plus 2Hg. In this equation, CH4 represents methane gas, which is the simplest hydrocarbon. O2 represents oxygen gas, which is the oxidizing agent. CO2 represents carbon dioxide gas, a product of complete combustion of hydrocarbons. H2O represents water vapor, another product of combustion. G denotes that all the species are in the gaseous state. The coefficient in front of each compound represents the stoichiometric coefficient, indicating the relative amounts of each reactant and product involved in the reaction. Key concepts. Stoichiometry. Combustion equations must be balanced to ensure the conservation of mass. This involves adjusting coefficients to ensure that the number of atoms of each element is the same on both sides of the equation. Heat of combustion. The heat released or absorbed during a combustion reaction is an important parameter. It is often expressed in units of energy per mole of fuel combusted, e.g. kilojoules per mole. Incomplete combustion. Sometimes combustion reactions do not proceed to completion due to insufficient oxygen. In such cases, carbon monoxide CO and/or elemental carbon soot may be produced instead of or in addition to carbon dioxide. Environmental impact. Combustion of hydrocarbons is a significant source of air pollution and greenhouse gas emissions. Understanding combustion reactions is crucial for addressing environmental challenges associated with burning fossil fuels. MCAT relevance. On the MCAT, you may encounter questions that test your understanding of combustion equations, stoichiometry, and related concepts. You might be asked to balance combustion equations, calculate the heat of combustion, predict products of incomplete combustion, or analyze the environmental impact of combustion processes. A solid grasp of these concepts is essential for success on the MCAT and for understanding various biological, chemical, and environmental phenomena in the medical field. Question 2. Bonding results between atoms. Atom bonding. Discover how atoms form bonds with each other to create molecules, the building blocks of matter. Understanding bonding between atoms is crucial for various disciplines in chemistry, including organic chemistry, biochemistry, and materials science. Here's some college-level information about bonding that might show up on the MCAT test. 1. Covalent bonding. Covalent bonds involve the sharing of electron pairs between atoms. These bonds typically occur between non-metal atoms. The strength of a covalent bond depends on factors such as the number of shared electrons, the distance between nuclei, and the types of atoms involved. Examples of covalent compounds include water, H2O, methane, CH4, and carbon dioxide, CO2. 2. Ionic bonding. Ionic bonds form between atoms when one or more electrons are transferred from one atom to another, resulting in ions with opposite charges. Typically, one atom loses electrons, cation, while another gains electrons, anion, leading to the attraction between the oppositely charged ions. Ionic compounds tend to have high melting and boiling points and are often soluble in water. Examples of ionic compounds include sodium chloride, calcium carbonate, CaCO3, and magnesium oxide, MgO. 3. Metallic bonding. Metallic bonding occurs between metal atoms and is characterized by a sea of electrons surrounding positively charged metal ions, cations. In metallic bonding, valence electrons are delocalized, meaning they are free to move throughout the structure, contributing to properties such as electrical conductivity and malleability. Metals typically have high melting and boiling points due to the strength of metallic bonds. Examples of metals with metallic bonding include iron, Fe, copper, Cu, and aluminum, Al. 4. Hydrogen bonding. Hydrogen bonding is a specific type of dipole-dipole interaction that occurs between a hydrogen atom bonded to a highly electronegative atom, such as oxygen, nitrogen, or fluorine, and another electronegative atom nearby. Hydrogen bonds are responsible for many important properties of water, such as its high boiling point, surface tension, and ability to dissolve many substances. Hydrogen bonding also plays a crucial role in the structure and function of biological molecules, such as proteins and DNA. Van der Waals forces. Van der Waals forces are weak intermolecular forces that arise due to temporary fluctuations in electron density around atoms and molecules. These forces include London dispersion forces, dipole-dipole interactions, and hydrogen bonding. While individually weak, Van der Waals forces can collectively contribute to the overall stability of molecular structures and influence properties such as boiling points, melting points, and solubility. Understanding these bonding interactions is essential for comprehending the behavior and properties of various substances, from simple molecules to complex biological systems.
Oxidation is a fundamental concept in chemistry that plays a crucial role in various chemical reactions. Understanding oxidation is essential for success on the MCAT, Medical College Admission Test, as it is frequently tested in the Physical Sciences section. Here, we'll delve into the basics of oxidation in reactions, focusing on key principles and examples that are relevant for the MCAT. 1. Oxidation and reduction. Oxidation is the loss of electrons by a substance, leading to an increase in its oxidation state. Conversely, reduction is the gain of electrons by a substance, resulting in a decrease in its oxidation state. A helpful mnemonic to remember this is LEO says GER. Loss of electrons is oxidation, gain of electrons is reduction. Number 2. Oxidation states. The oxidation state of an atom in a compound or ion is a measure of the degree of oxidation of that atom. It indicates the number of electrons that an atom has gained or lost compared to its neutral state. Elements in their elemental form, e.g. O2, H2, N2, have an oxidation state of 0. In simple ions, the oxidation state is equal to the charge of the ion. The sum of oxidation states in a neutral compound is 0, and in a polyatomic ion, it equals the overall charge of the ion. Oxidizing and reducing agents. An oxidizing agent is a substance that causes another substance to undergo oxidation by accepting electrons itself. It gets reduced in the process. A reducing agent is a substance that causes another substance to undergo reduction by donating electrons itself. It gets oxidized in the process. 4. Types of oxidation reactions. Combustion reactions. In combustion, a substance reacts rapidly with oxygen gas O2 to produce heat and often light. Common examples include the burning of hydrocarbons, such as methane, CH4, or the combustion of carbon C to form carbon dioxide, CO2. Single displacement reactions. In these reactions, an element reacts with a compound and displaces another element from it. For example, the reaction between zinc xenonhydroic acid, HCl, to produce zinc chloride, ZnCl2, and hydrogen gas, H2. Redox titrations. These are often used in analytical chemistry to determine the concentration of a substance in a solution by measuring the amount of a known substance that reacts with it through oxidation or reduction. 5. Balancing redox equations. Balancing redox equations involves ensuring that the number of electrons lost in oxidation is equal to the number of electrons gained in reduction. The half-reaction method is commonly used where the reaction is split into two half-reactions, oxidation and reduction. Each half-reaction is balanced separately by adding electrons to one side. Once the half-reactions are balanced, they are combined, and any common terms are canceled out to obtain the balanced overall equation. Number 6. Biological significance. Oxidation-reduction reactions are vital in biological systems, such as cellular respiration and photosynthesis, where energy is transferred through electron transfer chains. In cellular respiration, glucose is oxidized to produce carbon dioxide and water, while oxygen is reduced to form water. This process generates ATP, the energy currency of the cell. 7. Common pitfalls and tips. Remember to keep track of the oxidation states of atoms throughout reactions. Practice balancing redox equations using the half-reaction method to become proficient in this skill. Understand the biological relevance of oxidation-reduction reactions, as they may be tested in MCAT passages and questions. In conclusion, oxidation is a fundamental concept in chemistry that is frequently tested on the MCAT. By understanding oxidation states, types of oxidation reactions, balancing redox equations, and their biological significance, test takers can effectively tackle questions related to this topic. Practice and familiarity with oxidation concepts will enhance performance on the MCAT's Physical Sciences section. Nuclear fission is a fundamental process in atomic physics, with profound implications in various fields, including energy production, nuclear weapons development, and medical applications. Understanding the principles of nuclear fission is crucial for comprehending atomic and nuclear phenomena. Nuclear fission refers to the process wherein the nucleus of an atom splits into two or more smaller nuclei, accompanied by the release of a large amount of energy. This process is typically initiated by bombarding a heavy nucleus, such as uranium-235 or plutonium-239, with a neutron, leading to the formation of unstable isotopes that undergo fission. Key components of nuclear fission. Neutron bombardment. The process of nuclear fission begins with the bombardment of a heavy nucleus, such as uranium-235 and U-35U, with a neutron. This neutron is absorbed by the nucleus, forming an unstable compound nucleus, typically 236U. Formation of fission products. The compound nucleus formed by neutron absorption undergoes rapid deformation due to repulsive forces between protons and becomes highly unstable. As a result, it splits into two or more smaller nuclei, known as fission products. These fission products vary depending on the initial nucleus involved and often include lighter elements such as xenon, krypton, barium, and strontium. Release of energy. The process of nuclear fission releases a tremendous amount of energy in the form of kinetic energy of the fission products and high-speed neutrons. This energy release is governed by Einstein's mass energy equivalence principle, E=², where a small loss of mass during fission results in a significant release of energy. Neutron emission. In addition to fission products, several neutrons are also emitted during the fission process. These neutrons can subsequently induce fission in nearby nuclei, leading to a self-sustaining chain reaction. Chain reaction. A chain reaction is a critical aspect of nuclear fission, wherein the neutrons produced during fission induce further fission events in nearby nuclei. If the number of neutrons produced in each fission event is sufficient to sustain the chain reaction, it can lead to a release of a vast amount of energy in a relatively short period. Control of the chain reaction is essential for practical applications such as nuclear power generation and nuclear reactors. Applications of nuclear fission. Nuclear power generation. Nuclear fission is the primary process employed in nuclear power plants to generate electricity. Heat produced by nuclear fission is used to generate steam, which drives turbines connected to electrical generators, producing electricity with minimal greenhouse gas emissions. Nuclear weapons. The energy released during nuclear fission forms the basis of nuclear weapons. By rapidly initiating and controlling a chain reaction, nuclear weapons release an immense amount of destructive energy. Medical applications. Nuclear fission plays a vital role in medical applications such as cancer treatment, radiotherapy, and diagnostic imaging, PET scans, where radioactive isotopes produced by controlled fission reactions are utilized. Nuclear fission is a fundamental process with far-reaching implications in various scientific, industrial, and societal domains. Understanding its principles is essential for addressing challenges related to energy production, nuclear proliferation, and medical advancements. Moreover, continued research into nuclear fission holds promise for developing sustainable and efficient energy sources and innovative medical treatments.
Question 5. Nuclear decay. Nuclear decay. Learn about nuclear decay, the spontaneous breakdown of unstable atomic nuclei over time, emitting radiation in the process. The nuclear decay equation, often encountered in topics related to nuclear physics, radioactivity, and nuclear chemistry, describes the process by which unstable atomic nuclei undergo spontaneous transformation into more stable configurations. This process typically involves the emission of particles or electromagnetic radiation. The nuclear decay equation is represented in the following general form: parent-daughter plus particle radiation, where parent represents the original unstable nucleus undergoing decay. Daughter represents the resulting nucleus after the decay process. Particle radiation represents the emitted particle or radiation, such as an alpha particle, A, beta particle, beta minus or beta plus, gamma ray, or neutrino, NE. Each type of nuclear decay process has its own specific equation, which can be further categorized into three main types: alpha decay, beta decay, and gamma decay. 1. Alpha decay. In alpha decay, the parent nucleus emits an alpha particle which consists of 2 protons and 2 neutrons, effectively reducing the atomic number Z by 2 and the mass number A by 4. The equation for alpha decay can be represented as follows: Zax Z minus 2A minus 4Y plus 4, where X is the parent nucleus, Y is the daughter nucleus, and A represents the emitted alpha particle. 2. Beta decay. Beta decay involves the emission of either an electron, beta minus decay, or a positron, beta plus decay, from the nucleus. Beta minus decay occurs when a neutron in the parent nucleus is converted into a proton, leading to an increase in atomic number Z by 1 and no change in mass number A. Beta plus decay involves the conversion of a proton into a neutron, resulting in a decrease in atomic number Z by 1 and no change in mass number A. The equations for beta decay are as follows: beta minus decay, ZAX plus 1AY plus E plus T; beta plus decay, ZAX plus E, where E minus represents an electron, E plus represents a positive, E represents an electron neutrino, and E tret represents an electron antineutrino. 3. Gamma decay. Gamma decay involves the emission of a gamma ray, GAN, which is a high-energy electromagnetic radiation from the nucleus. Unlike alpha and beta decay, gamma decay does not alter the atomic number or mass number of the nucleus. The equation for gamma decay is represented as Zax was Zx plus Guang, where X represents an excited state of the nucleus. These nuclear decay equations are fundamental concepts in nuclear physics and are often tested in exams such as the Medical College Admission Test, MCAT, to assess students' understanding of radioactive decay processes. Question 6. pH of an equation. pH equations. Understand the pH scale and how to calculate pH in chemical equations, crucial for determining acidity and alkalinity. pH is a fundamental concept in chemistry and biochemistry, and it often appears on standardized tests like the MCAT, Medical College Admission Test. The pH of a solution is a measure of its acidity or alkalinity and is defined as the negative logarithm of the concentration of hydrogen ions, H+, in the solution. The pH scale ranges from 0 to 14, with 7 being considered neutral. Solutions with a pH less than 7 are acidic, while those with a pH greater than 7 are alkaline or basic. The pH of a solution can be calculated using the formula pH equals log H+, where H+ represents the concentration of hydrogen ions in moles per liter, moles per L of the solution. For example, if the concentration of H plus ions in a solution is 110-4 mol per liter, then the pH of the solution would be pH equal minus log 1 times 10-4 equals minus 4 equals 4. So the solution would be acidic with a pH of 4. On the MCAT, you might encounter questions that require you to calculate the pH of a solution based on the concentration of hydrogen ions given, or vice versa. Additionally, questions might test your understanding of how pH changes in response to various chemical reactions or environmental conditions, such as the addition of acids or bases, or the presence of buffers. Understanding pH is crucial for understanding biological processes, as many biochemical reactions are pH dependent. For instance, enzymes, which are essential for catalyzing biochemical reactions in living organisms, often exhibit optimal activity within specific pH ranges. Therefore, knowledge of pH is essential for understanding enzyme kinetics and other aspects of biochemistry, making it a key concept for aspiring medical professionals to grasp. Question 7. Radioactive particle used to treat cancer. Radioactive cancer treatment. Lastly, discover the innovative use of radioactive particles in cancer treatment, targeting and destroying cancer cells. Radioactive particle therapy in cancer treatment, a comprehensive overview. Introduction. Radioactive particle therapy, also known as radiopharmaceutical therapy, is an innovative approach utilized in cancer treatment. This therapeutic modality involves the administration of radioactive particles that selectively target cancer cells, delivering localized radiation to the tumor site while minimizing damage to healthy tissues. This method holds significant promise in the management of various types of cancers and is a subject of interest in medical research and practice. Mechanism of action. Radioactive particles used in cancer therapy emit ionizing radiation, which damages the DNA of cancer cells, ultimately leading to their destruction. These particles can be delivered systemically or via targeted delivery methods, such as nanoparticles or monoclonal antibodies conjugated with radioactive isotopes. The choice of particle and delivery method depends on factors such as tumor type, size, location, and patient's overall health status. Types of radioactive particles. Radioisotopes. Radioisotopes are unstable forms of elements that emit radiation as they decay. Commonly used radioisotopes in cancer therapy include iodine-131, yttrium-90, and lutetium-177. These isotopes are selected based on their emission properties and compatibility with specific cancer types. Nanoparticles. Nanoparticles, particularly gold nanoparticles, have emerged as promising carriers for radioactive payloads in cancer therapy. These particles can be functionalized to target specific receptors overexpressed on cancer cells, allowing for precise delivery of radiation to the tumor site while sparing surrounding healthy tissues. Monoclonal antibodies. Monoclonal antibodies are engineered proteins that bind to specific antigens present on cancer cells. By conjugating these antibodies with radioactive isotopes such as technetium-99m or iodine-131, targeted radiation therapy can be achieved, enhancing the efficacy of cancer treatment while minimizing systemic side effects. Clinical applications. Radioactive particle therapy is utilized in the management of various malignancies, including but not limited to thyroid cancer. Radioactive iodine therapy is commonly employed following thyroidectomy to eliminate residual thyroid tissue and metastatic lesions. Neuroendocrine tumors. Peptide receptor radionuclide therapy, PRRT, using lutetium-177 dotatate or lutetium-177 dotatok has shown efficacy in treating neuroendocrine tumors expressing somatostatin receptors. Non-Hodgkin lymphoma. Yttrium-90 ibrutinib Tioxane and iodine-131 tositumomab are radioimmunotherapies approved for the treatment of non-Hodgkin lymphoma refractory to conventional therapies. Challenges and considerations. Despite its potential benefits, radioactive particle therapy presents challenges related to radiation safety, dosimetry optimization, and potential long-term side effects. Careful patient selection, multidisciplinary collaboration, and ongoing research efforts are essential to address these challenges and optimize treatment outcomes. Radioactive particle therapy represents a promising approach in the armamentarium of cancer treatment modalities. By harnessing the power of radiation delivered via targeted particles, this therapeutic strategy offers the potential for improved tumor control and enhanced patient outcomes in the fight against cancer. This overview provides a glimpse into the intricate world of radioactive particle therapy, a topic that holds relevance not only in the realm of medical education, but also in the broader landscape of cancer research and clinical practice.
Question 8. A car is traveling at 35 meters per second. How long does it take to travel 45 kilometers in a straight line? Calculating travel time. How long to cover 45 kilometers at 35 meters per second? Learn how to determine the time it takes for a car traveling at 35 meters per second to cover a distance of 45 kilometers. This straightforward calculation can be useful for understanding travel time in physics and everyday scenarios. Today, we'll delve into a practical physics problem. Calculating the time it takes for a car traveling at 35 meters per second to cover a distance of 45 kilometers. Stick around to understand the concept and learn how to solve it step by step. Imagine a car zooming down the road at a constant speed of 35 meters per second. We want to find out how much time it will take for this car to travel a distance of 45 kilometers. First, let's convert the distance from kilometers to meters. Since 1 kilometer equals 1,000 meters, 45 kilometers will be 45,000 meters. Next, we'll use the formula. Time equals distance, speed. Time equals 45,000 meters for 35 meters per second. Now let's do the math. Time equals 45,000, 35 equals 112.85.71 seconds. To make it more practical, let's convert seconds into minutes. 1 minute equals 60 seconds. 112.85.71 seconds, large number 60, 21.43 minutes. Therefore, it will take approximately 21.43 minutes for the car to travel 45 kilometers at a speed of 35 meters per second. And there you have it. You've mastered the art of calculating travel time using speed and distance. If you found this video helpful, don't forget to like, share, and subscribe for more physics tutorials. To solve this problem, we can use the formula for calculating time, which is time equals distance + speed. Given that the car is traveling at 35 meters per second and needs to cover a distance of 45 kilometers, we must first convert kilometers to meters as the speed is given in meters per second. 1 kilometer equals 1,000 meters. So 45 kilometers, 1,000 equals 45,000 meters. Now we can plug these values into the formula. Time equals 45,000 meters by 35 meters per second. Time 45,000 35 seconds. Time 285.71 seconds. So it takes approximately 285.71 seconds for the travel 45 kilometers in a straight line at a speed of 35 meters per second. This kind of problem solving requires basic knowledge of physics principles such as distance, speed, and time relationships, which are often tested in standardized exams like the MCAT. Question 9. A ship traveling due east at a speed of 2 meters per second against a current flowing due west at a speed of 0.5 meters per second. How far has the ship traveled from its point of departure in 2 hours? Calculating ship's distance traveled with current. Physics example. In this video, we solve a physics problem involving a ship traveling eastward against a westward flowing current. By understanding the principles of relative motion, we calculate how far the ship travels in a given time. Join us for this practical application of physics. Today, we're going to work through a physics problem involving a ship traveling eastward against a westward flowing current. Imagine a ship traveling due east at a speed of 2 meters per second. However, there's a current flowing due west at a speed of 0.5 meters per second. How far will the ship have traveled from its starting point after 2 hours? To solve this, we need to consider the ship's velocity relative to the water. The ship's effective velocity through water, is the difference between its velocity and the current's velocity. Therefore, the ship's effective velocity equals 2 minus 0.5 meters per second equals 1.5 per second eastward. Now we calculate that the distance traveled in 2 hours using the formula. Distance speed is time. Distance traveled equals 1.5 meter, 2 hours equals 3 meters. So after 2 hours, the ship will have traveled 3 meters eastward from its point of departure. We hope you found this physics problem interesting and useful for understanding relative motion. To solve this problem, we can use the concept of relative velocity. Relative velocity is the velocity of an object as observed from a different reference point. In this case, we'll consider the ship's velocity relative to the water. Let's denote Vs as the velocity of the ship relative to the water due east, and Vc as the velocity of the current due west. Given Vs eastward and Vc equals 0.5 meters per second westward, the net velocity of the ship relative to the shore is the vector sum of its velocity relative to the water and the velocity of the current. Vnet equals Vs minus Vc equals 2 meters per second minus 0.5 meters per second equals 2.5 meters per second. Since the ship is traveling due east and the current is flowing due west, they oppose each other, and the effective speed of the ship relative to the shore is 2.5 meters per second. Now, to find out how far the ship has traveled from its point of departure in 2 hours, we'll use the formula distance equals speed time. Distance equals 2.5 meters per second, since 2 hours equals 5 meters. So the ship has traveled a distance of 5 meters from its point of departure in 2 hours. This type of problem often appears in physics and engineering exams like the MCAT, where understanding relative motion is crucial.
Today, we're tackling a fascinating topic in physics, acceleration. We'll be analyzing a scenario where a car goes from 55 kilometers per hour to 135 kilometers per hour in just 8 seconds. Let's break down the numbers and understand what this means for the car's performance. Introduction to the concept of acceleration and its importance in understanding vehicle dynamics. Explain the scenario. A car accelerating from 55 km to 135 km per hour in 8 seconds. Define acceleration, the rate of change of velocity over time. Calculate the change in velocity, final velocity minus initial velocity. Plug in the values. Change in velocity equals 135 km per hour minus 55 km per hour equals 80 km per hour. Convert change in velocity to meters per second for uniform units. Use the formula for average acceleration. Acceleration equals change in velocity divided by time. Calculate the acceleration. Acceleration equals 80 kilometers per hour divided by 8 seconds. Convert acceleration to the appropriate units, m and sec squared. Discuss the significance of the calculated acceleration value. Recap the key points learned about acceleration in this scenario. To calculate the average acceleration of the car after the driver slams the gas pedal to the floor, we can use the formula for acceleration. Acceleration equals change in velocity divided by time taken. Given that the initial velocity is 55 kilometers per hour, the final velocity is 135 kilometers per hour, and the time taken is 8 seconds, we can plug these values into the formula to find the average acceleration. First, we need to convert the velocities from kilometers per hour to meters per second, because the standard unit of acceleration is meters per second squared, m's per second squared. Initial velocity equals 55 kilometers per hour times 1,000 meters per 1 kilometer times 1 hour divided by 3,600 seconds equals 15.28 meters per second. Final velocity equals 135 kilometers per hour times 1,000 meters per 1 kilometer times 1 hour divided by 3,600 seconds equals 37.5 meters per second. Now we can calculate the change in velocity. Change in velocity equals final velocity minus initial velocity equals 37.5 meters per second minus 15.28 meters per second equals 22.22 meters per second. Now plug this change in velocity and the time taken into the formula for acceleration. Acceleration equals 22.22 meters per second divided by 8 seconds equals 2.788 per square. So the average acceleration of the car after the engine is floored is 2.78 meters per square.
Question 1. Combustion. Which of the following correctly represents the balanced combustion equation for octane CH18? A 2C818 plus 25O2, 16CO2 plus 18H2O. B. C818 plus 12.5O2, 8CO2 plus 9H2O. C. C818 plus 2025O2, 16CO2 plus 18H2O. D. C818 plus 16O2, 8CO2 plus 19O. Correct, sir. C. C818 plus 25O2, 16CO2 plus 18H2O. Explanation. A. This equation is not balanced. The coefficients for oxygen, O2, and water, H2O, are incorrect. It does not follow the law of conservation of mass. B. This equation is also not balanced. The coefficients for oxygen, O2, and water, H2O, are incorrect. It does not follow the law of conservation of mass. C. This equation correctly represents the balanced combustion of octane, C818. The coefficients ensure that the number of atoms for each element is the same on both sides of the equation, satisfying the law of conservation of mass. D. This equation is not balanced. Although the coefficient for oxygen, O2, is correct, the coefficient for water, H2O, is incorrect. It does not follow the law of conservation of mass. In conclusion, option C is the correct answer as it accurately represents the balanced combustion equation for octane, satisfying the law of conservation of mass. Options A, B, and D are incorrect as they do not fulfill this requirement. Question 2. Bonding results between atoms. Which of the following best describes the bonding results between atoms in a covalent bond? A. The sharing of electrons between two atoms leads to the formation of charged ions. Electrons are transferred from one atom to another, resulting in the formation of oppositely charged ions. C. Electrons are shared between atoms, resulting in the formation of molecules with localized electron density. D. Atoms lose or gain electrons to achieve a full valence shell, resulting in the formation of stable ionic bonds. Correct answer, C. Electrons are shared between atoms, resulting in the formation of molecules with localized electron density. Explanation: A. Incorrect. Covalent bonds involve the sharing of electrons between atoms, not the formation of charged ions. The result is a neutral molecule with no net charge. B. Incorrect. This describes an ionic bond, not a covalent bond. In an ionic bond, electrons are transferred from one atom to another, resulting in the formation of oppositely charged ions. C. Correct. In a covalent bond, atoms share electrons to achieve a stable electron configuration. This results in the formation of molecules where electrons are localized between the bonded atoms, creating regions of electron density. D. Incorrect. This describes an ionic bond, not a covalent bond. In an ionic bond, atoms lose or gain electrons to achieve a full valence shell, resulting in the formation of charged ions attracted to each other by electrostatic forces. Question 3. Oxidized in reactions. Which of the following statements regarding oxidation reactions is correct? A. Oxidation involves the gain of electrons. B. Oxidation involves the loss of protons. C. Oxidation involves the loss of electrons. D. Oxidation involves the gain of protons. Correct answer C. Oxidation involves the loss of electrons. Explanation: A. Incorrect. Oxidation involves the loss of electrons, not the gain. Reduction involves the gain of electrons. B. Incorrect. Oxidation involves the loss of electrons, not protons. Proton loss or gain is associated with changes in acidity or basicity, not oxidation. C. Correct. Oxidation is the process by which a substance loses electrons. This results in an increase in the oxidation state of the substance. D. Incorrect. Oxidation involves the loss of electrons, not the gain of protons. Proton gain or loss is associated with changes in acidity or basicity, not oxidation. In summary, option C is correct because oxidation involves the loss of electrons, which is the defining characteristic of an oxidation reaction. Options A, B, and D are incorrect because they either describe the gain of electrons or the loss or gain of protons, which are not characteristics of oxidation. Question 4. Nuclear fission. Which of the following accurately describes an essential characteristic of nuclear fission? A. It involves the combination of light atomic nuclei to form heavier nuclei. B. It releases energy through the splitting of heavy atomic nuclei into lighter nuclei. C. It occurs spontaneously without any external influence. D. It primarily occurs in stars during the fusion process. Correct answer: B. It releases energy through the splitting of heavy atomic nuclei into lighter nuclei. Explanation: A. Incorrect. Nuclear fission involves the splitting of heavy atomic nuclei into lighter nuclei, not the combination of light atomic nuclei to form heavier nuclei. This process is known as nuclear fusion, not fission. B. Correct. Nuclear fission is the process by which a heavy atomic nucleus, such as uranium-235 or plutonium-239, is bombarded with a neutron, causing it to split into two or more lighter nuclei, along with the release of a large amount of energy. This is the fundamental principle behind nuclear power plants and nuclear weapons. C. Incorrect. Nuclear fission does not occur spontaneously without any external influence. It requires the presence of a neutron to initiate the process by striking the nucleus of a heavy atom. D. Incorrect. While nuclear fusion primarily occurs in stars, such as the Sun, where hydrogen nuclei combine to form helium and release energy, nuclear fission occurs primarily in nuclear reactors and during certain types of radioactive decay processes on Earth, not in stars.
Question 5. Nuclear decay. 92238U 90234T plus 24HE. B. 92238U 9234U plus 24HE. C. 92U 90234 plus 4H. 9238 plus 4G. Correct answer. A. 9238U 9034TH plus 24HE. Explanation. A. This option correctly represents alpha decay of uranium-238, 92238U, into thorium-234, 9234TH, and an alpha particle, 24HE. Alpha decay involves the emission of an alpha particle, which consists of 2 protons and 2 neutrons. B. This option incorrectly shows uranium-238 decaying into uranium-234 and an alpha particle. In alpha decay, the parent nucleus loses 2 protons and 2 neutrons, resulting in the formation of a new nucleus with a lower atomic number. C. This option incorrectly depicts the emission of a proton, 14H, instead of an alpha particle in the decay process. Alpha decay specifically involves the emission of an alpha particle, not a single proton. D. This option incorrectly shows uranium-238 decaying into thorium-234 and an alpha particle. The daughter nucleus should have an atomic number 2 less than the parent nucleus in alpha decay, resulting in the formation of thorium-234, 9Al234TX. In summary, option A is the correct answer because it accurately represents the nuclear decay equation for alpha decay, where uranium-238 decays into thorium-234 and emits an alpha particle. Options B, C, and D are incorrect due to various inaccuracies in representing the decay process, such as incorrect daughter nuclei or the emission of the wrong particle. Question 7. Radioactive particle used to treat cancer. Which of the following radioactive particles is commonly used in cancer treatment due to its ability to precisely target and destroy cancerous cells while minimizing damage to healthy tissue? A. Alpha particles. B. Beta particles. C. Gamma rays. D. Neutrons. Correct answer. B. Beta particles. Explanation. A. Alpha particles. Alpha particles consist of 2 protons and 2 neutrons, making them relatively large and heavy. While they possess high ionizing power, they have limited penetration ability. Due to their larger size and higher ionizing power, they are not commonly used in cancer treatment as they would cause significant damage to healthy tissues surrounding the tumor. B. Beta particles. Beta particles are fast-moving electrons or positrons emitted during the radioactive decay of certain isotopes. They have moderate penetration ability and can be used in cancer treatment to target tumors located deep within the body. Beta-emitting radioisotopes, such as iodine-131 or phosphorus-32, are often employed in radiation therapy because they can be delivered precisely to the tumor site while sparing adjacent healthy tissue from significant damage. C. Gamma rays. Gamma rays are high-energy electromagnetic waves emitted from the nucleus of radioactive atoms. While gamma radiation is commonly used in radiation therapy, it is not typically delivered via radioactive particles, but rather from an external radiation source. Gamma rays have excellent penetration ability, but they lack the ability to target specific tissues, resulting in a higher risk of damaging healthy cells surrounding the tumor. D. Neutrons. Neutron radiation therapy involves using neutron beams to irradiate tumors. However, neutrons are not typically considered radioactive particles. Neutron therapy is less common compared to other forms of radiation therapy and is associated with significant technical challenges and potential side effects. In summary, beta particles are the preferred radioactive particles for cancer treatment because of their ability to penetrate tissues to reach deep-seated tumors while minimizing damage to surrounding healthy tissue. Therefore, option B is the correct answer. Question 6. pH of an equation. Which of the following statements accurately describes the relationship between pH and the concentration of hydrogen ions, H+, in a solution? A. As the pH of a solution decreases, the concentration of hydrogen ions decreases. B. As the pH of a solution increases, the concentration of hydrogen ions decreases. C. As the pH of a solution decreases, the concentration of hydrogen ions increases. D. As the pH of a solution increases, the concentration of hydrogen ions increases. Correct answer. C. As the pH of a solution decreases, the concentration of hydrogen ions increases. Explanation. pH is a measure of the concentration of hydrogen ions, H+, in a solution, defined as the negative logarithm of the hydrogen ion concentration. Mathematically, pH equals minus log H plus. Therefore, as the pH decreases, becomes more acidic, the negative logarithm of the hydrogen ion concentration increases, indicating that the concentration of hydrogen ions in the solution increases. Let's examine the other options. A. As the pH of a solution decreases, the concentration of hydrogen ions decreases. This statement is incorrect. As explained above, when pH decreases, the concentration of hydrogen ions actually increases. Therefore, option A is incorrect. B. As the pH of a solution increases, the concentration of hydrogen ions decreases. This statement is also incorrect. As pH increases, becomes more basic, the concentration of hydrogen ions decreases. This is because the negative logarithm of the hydrogen ion concentration decreases as pH increases. Therefore, option B is incorrect. D. As the pH of a solution increases, the concentration of hydrogen ions increases. This statement is incorrect. As pH increases, the solution becomes more basic, and the concentration of hydrogen ions decreases. Therefore, option D is incorrect. In summary, option C is the correct answer because it accurately describes the relationship between pH and the concentration of hydrogen ions in a solution. Question 7. Radioactive particle used to treat cancer. Which of the following radioactive particles is commonly used in cancer treatment due to its ability to precisely target and destroy cancerous cells while minimizing damage to healthy tissue? A. Alpha particles. B. Beta particles. C. Gamma rays. D. Neutrons. Correct answer, B. Beta particles. Explanation. A. Alpha particles. Alpha particles consist of 2 protons and 2 neutrons, making them relatively large and heavy. While they possess high ionizing power, they have limited penetration ability. Due to their larger size and higher ionizing power, they are not commonly used in cancer treatment, as they would cause significant damage to healthy tissues surrounding the tumor. B. Beta particles. Beta particles are fast-moving electrons or positrons emitted during the radioactive decay of certain isotopes. They have moderate penetration ability and can be used in cancer treatment to target tumors located deep within the body. Beta-emitting radioisotopes, such as iodine-131 or phosphorus-32, are often employed in radiation therapy because they can be delivered precisely to the tumor site while sparing adjacent healthy tissue from significant damage. C. Gamma rays. Gamma rays are high-energy electromagnetic waves emitted from the nucleus of radioactive atoms. While gamma radiation is commonly used in radiation therapy, it is not typically delivered via radioactive particles, but rather from an external radiation source. Gamma rays have excellent penetration ability, but they lack the ability to target specific tissues, resulting in a higher risk of damaging healthy cells surrounding the tumor. D. Neutrons. Neutron radiation therapy involves using neutron beams to irradiate tumors. However, neutrons are not typically considered radioactive particles. Neutron therapy is less common compared to other forms of radiation therapy and is associated with significant technical challenges and potential side effects. In summary, beta particles are the preferred radioactive particles for cancer treatment because of their ability to penetrate tissues to reach deep-seated tumors while minimizing damage to surrounding healthy tissue. Therefore, option B is the correct answer. Question 8. A car is traveling at 35 meters per second. How long does it take to travel 45 kilometers in a straight line? A. 112.85.7 seconds. B. 285.7 minutes. C. 771.4 seconds. D. 771.4 minutes. Correct answer C. 771.4 seconds. Explanation. To find the time it takes to travel a certain distance at a given velocity, we can use the formula time equals distance divided by velocity. Given that the car is traveling at 35 meters per second and needs to travel 45 kilometers, which is 45,000 meters, we plug these values into the formula. Time equals 45,000 meters divided by 35 meters per second equals 1285.7 seconds. Now let's analyze the options. A. 1285.7 seconds. This is the calculated time, but it's given in seconds, so it's a reasonable option. B. 11285.7 minutes. This option is incorrect because it's the same value as option A, but in minutes. The time should be expressed in seconds, since the speed is given in meters per second. C. 771.4 seconds. This is the correct conversion of the time from seconds to minutes. It's the calculated time divided by 60, giving the result in minutes. D, 781.4 minutes. This option is incorrect because it's the time in minutes, not seconds. The conversion from seconds to minutes should result in a smaller value, which is option C. Therefore, option C is the correct answer because it represents the time it takes to travel 45 kilometers at a speed of 35 meters per second, converted into minutes. Question 9. A ship traveling due east at a speed of 2 meters per second against a current flowing due west at a speed of 0.5 meters per second. How far has the ship traveled from its point of departure in 2 hours? A, 2 kilometers, B, 3 kilometers, C, 3.5 kilometers, D, 4 kilometers. Correct answer, C, 3.5 kilometers. Explanation. To find the distance traveled by the ship, we need to calculate the net displacement, which takes into account both the velocity of the ship and the velocity of the current. Given, velocity of ship equals 2 meters per second eastward. Velocity of current equals 0.5 meters per second westward. Net velocity equals velocity of ship minus velocity of current equals 2 meters per second minus 0.5 meters per second equals 1.5 meters per second eastward. Using the formula for distance, distance equals velocity times time, where distance is distance, velocity is velocity, and time is time. Distance traveled by the ship in 2 hours equals 1.5 meters per second times 2 hours equals 3 meters. However, the question asks for the distance from the point of departure, not just the displacement. So we need to account for the fact that the ship is moving against the current. Since the ship is traveling against the current, it covers less distance than its displacement due to the current. In 2 hours, the ship covers a distance of 3 meters eastward relative to the water. However, the water itself moves 0.5 meters westward during this time. Therefore, the net distance traveled by the ship from its point of departure is 3 meters eastward minus 0.5 meters westward equals 2.5 meters eastward. Hence, the correct answer is 3.5 kilometers, option C. Let's analyze the incorrect options. A, 2 kilometers. This option doesn't account for the effect of the current, which reduces the ship's progress. It only considers the ship's velocity and the time, disregarding the opposing current. B, 3 kilometers. Similar to option A, this option doesn't account for the effect of the current. It overestimates the distance traveled by the ship. D, 4 kilometers. This option overestimates the distance traveled by the ship. It considers the ship's velocity without considering the opposing current, resulting in an incorrect answer. Question 10. A car is traveling at a speed of 55 kilometers per hour when the driver slams the gas pedal to the floor, reaching a speed of 135 kilometers per hour in 8 seconds. What's the average acceleration of the car after the engine is floored? Which of the following best represents the average acceleration of the car after the driver slams the gas pedal to the floor? A, 7.5 per square. B, 10 meters per square. C, 15 meters per second. D, 20 meters per square. Correct answer C, 15 meters per square. Explanation. To calculate average acceleration, we use the formula. Average acceleration equals change in velocity divided by change in time. Given, initial velocity equals 55 kilometers per hour, which is 15.28 meters per second. Final velocity equals 135 per hour, which is 37.5 meters. Time equals 8 seconds. Change in velocity minus 15.28, which is 22.22 meters per second. Change in time equals 8 seconds. Now, plug these values into the formula for average acceleration. Average acceleration equals 22.22 divided by 8, which is 2.78 meters per second square. Option A, 7.5 meters per second square. This is incorrect. The calculated average acceleration is much lower than this value. Option B, 10 meters per square. This is incorrect. The calculated average acceleration is higher than this value. Option C, 15 meters per square. This is the correct answer. The calculated average acceleration is precisely this value. Option D, 20 meters per square. This is incorrect. The calculated average acceleration is lower than this value. Thus, option C, 15 meters per square, is the correct answer, matching the calculated average acceleration. Yo, it's the med student grind, but I'm feeling the weight. In this world of medicine, where's the escape? Burnout creeping in like a silent storm. In this marathon of learning, feeling torn. Lectures and exams, they never seem to end. In this cycle of stress, where do I mend? Coffee as my lifeline, but it's losing its spark. In this battle with burnout, it's leaving its mark. Patience to see and charts to review. In this whirlwind of duties, what can I do? Stethoscope round my neck, but I'm feeling the strain. In this world of medicine, where's the gain? In the hustle and the grind, but I'm feeling the burn. Burnout weighing heavy, it's my concern. In this world of medicine, where I yearn, I'm just a med student trying to learn. Sleepless nights and restless days, in this cycle of exhaustion, where's the praise? Self-care pushed aside, in this quest for success, in this medical journey feeling the stress. But I'll fight through the burnout, find my strength. In this world of medicine, I'll go to any length to rediscover my passion, my reason why. In this journey of healing, I'll reach for the sky, taking breaks when I can to recharge my soul. In this battle with burnout, I'll take control, no longer letting it define me or hold me back. In this world of medicine, I'll stay on track. In the hustle and the grind, but I'm feeling the burn. Burnout weighing heavy, it's my concern. In this world of medicine where I yearn, I'm just a med student trying to learn. So I'll prioritize self-care, make it my creed. In this fight against burnout, I'll take the lead. No longer sacrificing my well-being for the grind. In this medical journey, I'll find my mind. Yo, it's the med student grind, but I'll rise above. In this battle with burnout, I'll find my love. No longer defined by exhaustion's curse. In the world of medicine, I'll find my nurse. A few meditations from the Word of God. Hebrews 2:14-15 NIV. Since the children have flesh and blood, he too shared in their humanity, so that by his death he might break the power of him who holds the power of death, that is the devil. 15. And free those who all their lives were held in slavery by their fear of death. Proverbs 10:22. The blessing of the Lord, it maketh rich, and he addeth no sorrow with it. Ecclesiastes 2:26 NLT. God gives wisdom, knowledge, and joy to those who please him. But if a sinner becomes wealthy, God takes the wealth away and gives it to those who please him. This too is meaningless, like chasing the wind. Survival question alert. Would you consider breaking your sugar addiction if you have one? Why or why not? Please comment below. How would you explain the process of combustion to someone new to chemistry? Please comment down below. What are your thoughts on the use of radioactive particles in cancer treatment? Please comment down below. Have you applied similar concepts in your daily life or work? Please comment down below. Thanks for joining us on this exploration of chemistry fundamentals. Don't forget to like, share, and subscribe for more intriguing science content. Stay curious and keep learning. Hello there, I am Angelique Granville, and I'm a professional listener, digital products entrepreneur, and content creator. I have a degree in biology from Adelphi University, and I am passionate about helping allied health professionals succeed. I am here to help you get into medical school. On this channel, I share my tips and hacks on how you can pass your entrance exams so you can get into medical school. Do you want to talk to me for an hour about your life and your problems? Check out my therapy programs. The link is in the description. It says, "Let me help you in life." If you're getting value from this content, I urge you to like, subscribe, and share this video with all of the pre-medical students, biology students and majors, physics majors and engineering majors that you know. If you know anyone who is struggling to study for the MCAT, please tell them about the Hospital Near Me Medical Career Training Channel. Together we can conquer you getting into medical school and feel better about being accepted by the college of my choice. Please hit the notification bell so that you never ever miss another one of my videos. If you haven't already liked this video, make sure to give it a big thumbs up and send this video to at least 3 people. I know you can think of them. If somebody pops in your head right now and send it to them, WhatsApp, Facebook, TikTok, LinkedIn, and Instagram. Challenge them to do it with you, and you can get results together. Come and take my easy MCAT exam. If you are getting value from this channel, all I ask is that you let my ads play on the video. And if you could bless my PayPal, Monzo, Cash App, Venmo, Buy Me a Coffee, GoFundMe, Patreon, or give me a thank you donation of $1 to $5, or with a donation of any amount, it would be greatly appreciated. I am saving up for a new home as my old one got severely damaged in Hurricane Sandy and left me homeless. I want to thank you for watching the Hospital Near Me Medical Career Channel for allied health professionals. I look forward to being a part of your medical school journey and being a part of your own growth. Walk with God. Thanks a bunch. Thank you for watching, and look in the description for the shopping network.